Hello? Hello?
Hi.
Hi.
Hi. Okay, we'll start now.
Okay.
You can see my screen now, right? Okay. Okay, everyone's here? Okay, we shall start. Okay, so do anyone have any ideas for the homework problems? The first problem was t primes, and the second problem was get everything. If anyone solved it from the last time or have any ideas, just say. And for the new people, I'll give you 3 minutes to read it. Okay. Um, so 3 minutes to read t primes. Okay, we'll start with problem t primes. I'll send the link in the chat now. Take 2 to 3 minutes to read it, think about it, and discuss it with me. Okay. Okay, now we should have read it. So the problem gives us uh, an integer n, and then it gives us n numbers. Each number is between 1 to 10 power 12. Okay, we want to find if this number is t prime or not. And what's the definition of t prime here in the problem statement? So the definition of t prime is that it has exactly three distinct prime divisors. So something like um, actually it has exactly three distinct positive divisors. Okay, so something like four. So what are the divisors of four? They are one, two, four. Okay, something like nine. They are one, three, nine. Something like 25. So all of these are t prime numbers. Okay, but for example, 10 is not t prime because it has 1, 2, 5, 10. These are four divisors. Okay, so it should have exactly three distinct positive divisors like 4, 9, 25. 10 is not. Okay, do anyone have any ideas how to solve this problem? How to
Uh,
find if a number is t prime or not? Yeah, just go. Yeah.
if it should be a product of two prime numbers, then it can have only three, including those two primes.
Sorry, can you put the mic closer? I cannot hear you.
Okay, so I guess it should be a product of two prime numbers. Then only it can have three uh, distinct products. Like for example, 9 it is 3 and 3. It is a product of two prime numbers.
Yes.
So,
Okay. Yes. Yes, you're correct. Um, yes, that's right. So the number is t prime number if and only if it has exactly two prime divisors. Okay. Actually, it has one prime divisor of power two. So it's so t prime is equal to some prime squared. That's it. Why is that? Because if we have one prime, so let's prove this. So if we have one prime, so if the number equals if x equals to p, p power one, then the number of divisors will be one and p, right? So if x equals to some p1 times p2, so if x equals to the multiplication of two prime numbers, then the divisors should be 1 and p1 and p2 and p1 times p2. Okay, so there are four divisors. So this have two divisors, and this have two divisors. But what if x equals to p power 2, 1p only? So this should have 1 as a divisor, and p as a divisor, and p times p, which is p square, as a divisor. Okay, so x should be only this case. So this is t prime. This is a t prime number where it has exactly one prime divisor squared. Okay, so let's look at the constraints of the problem. So the one you said to me, anyone have any ideas how to check if the number has exactly one prime divisor with a power of 2? How can you do that, given that the constraints for x is 10 power 12? Any ideas? So let's take the input first.
uh, I guess we can take the numbers from 1 to square root of that number and multiply and see whether it matches with the number.
Um, I don't quite understand what
So,
exactly should we do.
so if the input is x, so we'll
Okay.
iterate from 1 to square root of x, and for each number we'll multiply with and check if it's a prime number. We'll get the prime numbers from 1 to square root of x, and
Okay.
if we'll do a square and see if it is matching with the number.
But how are we? How could we be certain that it has exactly one prime divisor? So now we are checking. So if it's something like 100, what should we do now? So we will check from 1 to 10, right? You are saying that we'll check from 1 to 10.
Yeah, from 1 to 10.
And then at 10, the square of 10 will be 100. Uh, but how could you check that that
Now,
100 has
now that we'll get the prime numbers from 1 to 10.
yes, okay, and then
Then we'll see the square of that. So the square of that number should be a t prime. So it falls below 100. Whatever square we are doing from 1 to 10 will the product of the number will fall below 100. So that should be a t prime since we are multiplying
yes,
prime into prime.
yes, I got you. Okay, so yes, you're right. So here constraints is n is up to 10 power 12. So we'll get the maximum number of n, okay? Actually up to 10 power 5. And x is up to 10 power 12. So if we did this approach that you said, we have n numbers and each containing x, which is 10 power 12. So the complexity will be of n times square root of x, right? So n times square root of x for these constraints for sure will not pass because it will be like 10 power 11 operations, okay? So this will time limit exceed. So we cannot do this. We want a very faster approach. So So a fast approach should be to know whether x is t prime or not in just O of 1 or O of log n, because n is very large. Okay, so we want to do something to check x, if x is t prime or not, but very fast. We want to make this very fast. Okay, uh, let's take some x equals to 9. I want to check if 9 is t prime or not. One condition is that if we took the square root of x, so square root of x, if square root of x is prime, like you said that we'll check every number from 1 until square root of x and multiply it by 2. But why not just check square root of x at the first time? Check if square root of x is prime, and then if it's prime, and of course if x is perfect square, so if x is perfect square and so if x is perfect square means that it has an integer square root. Okay, so if square root x is an integer, and if it's prime, then we're done. Then x is t prime. Then x is t prime. Do you all agree with this? So here let's check for 9. The square root of 9 equals 3. So here 9 is perfect square and 3 is prime. So that's it. So here 9 is t prime number. Okay. So now we could just take for after taking every x, for every x we'll just take the square root of it and then check if it's prime or not. That's it. Okay. But how to check if a number is prime or not? We said it the last time, I guess. So to check if a number is prime or not, a certain number is prime or not. So given x, or just make it y. So given y, we want to check if y is prime or not. So we'll make here a function that's called is prime, and it'll be given. Okay, let it n. So if we want to check if n is prime or not, if we want to check if any number is prime or not, then we'll check for all of its divisors. If it has any divisor, then it's not prime for sure, right? So we'll check until square root of that number. So explain the last time that we want to check for all numbers until n. We'll check for all numbers until only square root of n, because after this doesn't matter at all. Okay. So if n is divisible by any number until square root of n, then we'll just return false, because this is not a prime. But if the loop has finished, equals 0. If the loop has finished and we didn't return false, then for sure this number is prime, right? So here we have a function that checks if a number is prime or not, and the runtime of this function is O of square root of n. Okay, so if we are given, so now let's calculate. Let's check the complexity for the whole algorithm. We are given n, and for each n we are given x, and x is up to 10 power 12, like we said. 10 power 5. So here the complexity should be O of n multiplied. So multiplied by what? Multiplied by the operations that we do for every x. So for every x, we take the square root of it, which is 10 power 6. So square root of x. So I'm saying 10 power 12, 10 power 6 because this is the maximum, this is the bounds, okay? So I'm taking the largest numbers possible to just compute the complexity, okay? 10 power 6. So the square root of 10 power 6. And we are checking if this square root is prime or not. So the complexity of this function is square root of x. So square root of this square root will be 10 power 3. Okay, you get it? So we'll check if this square root is prime or not. So it will be square root. So it will be 10 power 3. Okay. So for prime checking, it will be 10 power 3. So this will be square root of x. Okay, so it will be O of n square root of n. Okay, so fourth root of n. So it will be,
Can you
yes,
explain
say.
more about 10 to the power 3? Didn't get on that. How is it 10 to the power 3?
Sorry, what you say again?
Now, can you once more explain on that 10 to the power 3? So, got till 10 to the power 6, square root of x equals 10 to the power 6, but how is that prime checking is 10 to the power 3? 10 raised to 3.
Okay, I'll say. Okay, so there is one asking in the chat, which question are you trying to solve? Okay, so I sent the link here. It's in the chat. So the first question I sent in the link in the chat here. If you can't see it, just tell me. Yes. Okay. So someone sent it. I think I'll send the link again just to be sure. So now you ask the question how the prime checking is 10 power 3, right? So uh, first, do you understand this function, or this is your problem? So your problem is in this function, right? Don't quite understand.
Yeah, that understood. That's yeah.
Okay, so you don't understand. Okay, so I'll explain again.
No, I understood that 10 the square root problem I understood. I understood till 10 raised to 6. So we are getting a square root, so that will be 10 power 6. After that, that prime checking 10 power 3. So that point I didn't understand. Line number 25.
Yes, okay, so I don't know what's the problem. Okay, so here, square root of x is 10 power 6, okay? And if we are checking for any number, let's, uh, let's call it n. If we are checking for any number, if it's prime or not, this will take a complexity of o square root n, okay? So if we are checking for square root x, so here we are checking is prime square root x. So here we are checking if the square root of x is prime or not. So square root of x is 10 power 6, right? And the complexity of is prime is square root of whatever here. We'll take the square root of it. Okay, so the complexity of this will be square root of, of so it will be square root of this thing. Okay, so it will be square root of x. So what don't you understand exactly? Just
Okay, got it now. Yeah, got
okay,
it.
got it. Okay. So here the complexity is of n square root of x, which should be fairly like 10 power 5 times 10 power 3, which is 10 power 8. Okay, so now since this is an easy problem in codeforces, not very hard, so this 10 power 8 operations should pass. Okay, so the constraints for this problem are not very high, so 10 power 8 should pass. It will be like fairly 1 second. Okay. So here a simple algorithm is we're checking if every prime, if the square root of every x is prime or not, and then print yes or no, then this will pass. But this is very slow, so this is a very critical. This is very critical point. So we want to make it even faster. Okay. So how to make this even faster? I'll explain now. So there is an algorithm called sieve. Let's explain it. Did anyone heard about sieve? Okay, I guess not. So sieve is a powerful algorithm that pre-computes the prime numbers until some n. Okay, so if n, so pre-computes prime numbers numbers are 10n, okay, and n could be as large as, as 10 power 7. Okay, so if we observed x, which is until 10 power 12 for our problem, we want to know if square root of x is prime or not, which is 10 power 6. So we are only interested from for numbers from 1 to 10 power 6 only. We don't go beyond that. Okay, so we're interested to find uh, we are interested to know every prime number from 1 to 10 power 6. Okay, so we will make sieve from 1 to 10 power 6, and I'll explain now how sieve works. So if we have something like an array here called boolean of p, this is of size 10 power 6, for example. So if I called p of x, yes, if I called p of x, it should be equals 1 if x is prime. Else, it should be equals to 0. Okay. So I want to pre-compute this. I want to add values, add boolean values to this array to make it if for any number, if it's prime, then it will have 1, and if it's not prime, it will have 0. But how could you calculate this? It's a very simple algorithm. So we said that we can check for every number if it's prime or not in square root of n. So if we have n up to 10 power 6, and we will check for every number from 1 to n if it's prime or not, then this will take 10 power 6 times square root 10 power 6, which is um, which is 10 power 8. But sieve works in a very powerful complexity, and the proof for this complexity is quite hard for now, so we'll not get to the proof for the complexity now. But the complexity for sieve is n log n. If you don't know what this means, so log n, this is a very fast. So it's not log times log, it's log. So it's nearly a constant. So if n is 10 power 7, so log 10 power 7, let me check that. To 10 power 7. So log 10 power 7 is like 23, and log 23 is just like constant, so it's like 4 or something. Log. Okay, so log 23 is a very small number, so it's like 5 or something. So here, if we have n is up to 10 power 7, so of n log 10 power 7 should be approximately 10 power 7 times some constant. So it will be very fast, okay? But here we are calculating until n up to 10 power 6, because this is our maximum bound. So this will be approximately 10 power 6 operations, okay? So let's explain sieve now. So here's the complexity for sieve. So sieve works like this. I'll just go ahead into the code. Okay, let's go. So I'll make m equals to our maximum number, which is 10 power 6, and I'll make it plus 1. And then I'll make a boolean array called p of size m, which will store if every prime is if every number is prime or not. Okay. So how the algorithm work is we loop we loop through every number from 2 to square root of m. Okay. So if I is prime number, so at first at first I'll make every number as prime number in sieve initially. Okay, so how sieve works is that we go for every prime number and then eliminate all its multiples. Okay, so if 2 is prime number, then for sure all of its multiples is not prime number. So 2 will eliminate, so it will remove 4, 6, 8, and so on, 10, 12, and the same thing for 3. So 3 will eliminate 6, 9, 12, 15, and so on. So this is only what sieve does. So what sieve does is that we initialize every number as if it's prime number. Okay, so here this fills all the array with ones. Okay, and then we pass through every prime number that is still prime, and then eliminate all of its multiples. Okay, so we'll pass into and then eliminate all of its multiples here, and then we'll find three, eliminate all of its numbers, and then we'll go to 4, but it's not prime, so we'll not continue. 5 is prime, so we'll eliminate all of its multiples. Okay, and so on and so on. So here, if p of I, so if p of I, that means if it's prime. So if p of I is prime, then we will eliminate all of its multiples. Means remove it from the prime Boolean array. Okay, so we'll make another loop that passes through all the multiples of I. So for int j equals I plus I. So the first multiple of I is I times 2, which is I plus I. So j is more than or equals n, j plus equals I, and then p of j equals to 0. So that's it. So this how C works. And you might ask me why you are looping until square root only, because like we said here, to know if a number is prime or not, or to check for divisors of a number, we don't need to pass after square root of that number. Okay, so if for example there is a number after square root of m, then I must have checked it. So if it's not prime, then I must have checked it before the square root. Okay, so I'm just passing um, for square root numbers only. Okay, so I'm just passing until square root of m. Okay, and here I'm checking if it's prime, then I'm eliminating all of its prime, all of its multiples. Okay, but first, after we initialized every number with prime and then we eliminated every non-prime number, there is still one that we didn't eliminate, which is 1, which is 1 itself. So p of 1 will be equal to 0 because 1 is not prime number. Okay, so before moving on to the next step, do you all understand sieve? Should make sure that you understand.
Why are we
If you
starting
have any
from
questions,
j equals I into I? I plus I.
okay. So now we are sure that p of I is prime. So we want to eliminate the first multiple of I, right? So the first multiple of I is I times 2, right? So we're eliminating. We are, like we said for 7, for example, we are eliminating 7 times 2, which is 14, and then 21, and then 28. So we're eliminating all of its multiples. So the first multiple for I is I times 2, and then for every time I'm adding I. I'm adding I. Okay, did you get this or not?
Okay.
Okay. Okay. So here how C works. So now if you called any p of x, so if it's 1, then this is prime. If it's 0, then this is not prime. Okay. So now I'll take the input. So I have n here. So let's check the input. So we'll take n and then x numbers. Okay. Okay, so there's someone asking log base 2 or 10. It's log base 2. So for here in computer science, for every log we are talking about, it's log 2. Okay, log base 2. there is no log based. We're not talking about log based in the complexities. It's rarely happens. Okay, so because if everyone have any question, just speak to be easier because I don't look at the chat very often. Okay, and someone says it's he who wrote this. Yes, that's right. So x is up to 10 power 12. So we should take it as long. And then we want to check. So now we have two conditions. The first condition if x is perfect square. Okay, and the second condition is if square root x is prime. So here we have these conditions. They must meet. So the first condition is x is perfect square, means that we cannot take something like 10 or 7 because they are not perfect squares. And square root of x is prime. So how to check if x is perfect square or not? It's actually quite easy. We'll make another integer called square. Okay, let's make it square. And then we'll make what's this? And then we'll put square equals to. We have a function in C++ that computes the square root of a number. So the square root of a number can be calculated in O of n. Okay, so this function calculates the square root of it in O of log n. So it's a negligible time. So O of log x. It's not important. Okay. So here, since we have the square root of x, to check if x is perfect square or not, we just make this. If square times square equals to x, so then this for sure is perfect square. So what does that mean? So square here is an integer. Okay, so long is an integer. But if I have something like 10, the square root of 10 is not integer, right? So square root of 10 should be something like 3 point something. Okay, so the square root of 10 is 3 point numbers, but this integer will just store the integer part. Okay, so it will remove all the decimals, so it will be just 3. So square root of 10 will be stored here as 3. So if we multiply 3 by 3, it's not equals to 10. It will be not equals to 10. So this is false. Okay, but if we have something like 9, so this condition will be true. Okay, so that's why we store the square root as an integer. Okay, so here is the first condition, and the second condition is to check if this square is actually prime or not. Okay. Uh, so my screen is not visible now, right?
Yes, it's not visible.
Okay, now it's visible. It should be.
Yes, Emma.
Okay, it's visible. Okay. So now this condition, if it's met, then we'll print yes. So if the number is perfect square, and if the square of it is prime, then we'll just print yes. Okay. So that's it. Here we solved. Okay, let's leave this. Or just leave it. Okay. Okay, so everything should be fine now. Let's try this.
There is an error in line initializing the
Hmm.
in line 21 int I equals 2.
Yes. Okay. Int I equals 2 items that hold G equals items 2 Okay, so here it should be smaller than m. Okay, everything should be okay. Okay. Okay, so it printed. Okay. So let's remove this for now because it's not important anymore. Mm, So everything should be okay. Let's try some cases. Let's try 1 and 2, 9, 10. Okay, so no, yes, no. Okay, let's try something like 25. Yes, okay. So let's submit. Hmm. Okay, accepted. Okay, here's the link to the submission. Sent it in the chat. Okay, let's move to the second homework problem, which was called get everything. So this problem was given homework last time. Anyone solved it? Okay, I'll give for the new ones. I'll give 3 minutes to read it, understand it, and then after this we'll discuss it. Okay, I'll send the link here in the chat. Okay, I think you should have read the problem now. Um, let's say the statement. We have n locked treasure boxes, okay, numbered from 1 to n. And there is a shop that sells m keys, and the cost for the ith key is a of in, okay. And then we are given which treasure boxes that this key unlocks, okay. So for every, let's do this. So we have n treasure boxes from 1 to n, exactly n treasure boxes, and you are given m keys. And then for every key we have a cost, and the boxes that it can unlock. So if I have a key that costs 7, and then it can unlock treasure boxes. It can unlock treasure boxes 1 for like 8. So if n is up to 10 or something, and then this key unlocks 1, 4, and 8. Then I can unlock 1, 4, and 8 at the same time with cost 7. Okay, so it's not 7 for every box. So it's 7 for all of the boxes. So I could unlock all of them, and then I'll just pay 7. Okay, so that's it. Um, so we need to know how to unlock all of the boxes. So if n is up to 10 for example, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make it boxes. So if the boxes are up to 10 and I'm given some m keys, I have to calculate the minimum cost to unlock all of these boxes. Okay, so let's take an example here. If I have m equals to 2, so I have 2 keys. The first key is at cost 2, and the second key is at cost 3. And this key unlocks boxes from 1 until 10, until 9. And this key unlocks boxes from 2 until 10. And then I have another, so let's make this 4, let's make this 3. And then I have another box cost 1 that unlocks treasure box 1. So what should be the strategy to get the minimum cost such that we unlock all the boxes? So it's clear here that we should take, the only option here is that we should take these 2 boxes, because this will unlock the first these 2 keys, because this will unlock the first box here 1, and then this will unlock from 2 to 10 at cost 4. Okay, so the cost will be 1 plus 3. So how do you think we could get the minimum cost to unlock all of the boxes? So how to choose the keys such that we'll have the minimum boxes? Any ideas how to do that?
I think using dynamic programming, it's optimization problem. So we can use dynamic program like either include the key or not include the key. And once all the boxes are included, we will do comparison, like whichever will be the minimum cost.
Yes. Yes, but yes, you're right. So if you did dynamic programming, and then for every key we choose whether to choose it or not. But how to know? So if for example I'm at the second at the fifth key or something, and then I choose it. So how to know the keys before me? So how to know if I choose keys before me or not? So let's say I am at key number 5. At key number 5. and then it unlocks only from 1 until 9. But I have a key smaller than 5 that I have chosen in any state that unlocks 10. So how to know if I'm standing at the state for the DP? How to know if I have unlocked the last if I have unlocked any treasure box or not? So
We can use like array or something where we can track which are not unlocked. Like we will go on removing the boxes which we are unlocking from the array, and if it is become nulls, we are know that we have unlocked all the boxes.
okay, so since we are given n is very small, so this is a very hint to the solution. You said yes, like 10 power 5 or something. It would be impossible to store for every state if I have visited any box or not. But n is up to 12, so I could store an integer of size 2 power 12 that have only bits. So the integer have bits of 0 and 1s, right? Let's make this smaller. So and every bit determines if this box is visited or not. So the first bit determines if the first box unlocked or not. So 1 means unlocked, 0 means not unlocked. 1 means unlocked, 0 not means unlocked. So an integer of up to 2 power 12 should be enough to store all of the information we need. Okay, so the DP will be of size m times 2 power 12. M is the number of keys, and 2 power 12. No, not 2 power 12. It will be of size 2 power 12. Yes, 2 power 12. Okay, so this will store an integer that have the bits that stores if any box is unlocked or not, and this will store the key that we're standing at right now. Okay, and then we'll just for every state we check whether we can take this key or not, and then if we took this key, then we'll update this bit, this integer, and then update the bits that have an unlocked boxes. Okay, so it will be something like this. We'll make it in solve to return an integer, of course. Let's make the variables first. Okay, m is up to 10 power 3. Okay. Then. So, okay. So first we'll take n, and then m, and then we want to make some arrays here. So the first array will be the let's make const int m equals 183. So the first array will be equals to val of m. So this array stores the costs for every key. Okay, let's make it costs. So this array stores the cost for every key, and we have keys until 10 power 3. So it will be 10 power 3 of size 10 power 3. Okay. And then while m minus minus, I'll just take for every m, I'll just take the cost and then the number of boxes that it could unlock. Okay, so here let's see, and then let's make this int I. Cost I equals c. Okay, so here I looped through the keys, and then I took the costs for every key, and then I should take another number that have the another number B that have the number of boxes that it could unlock. Okay, let's make this B. So here the question: how to store exactly the boxes. So if I store the boxes in array like this, so the first element will be box 1, the second element will be box 2, and so on. But this is not efficient because in the DP we are treating masks. Okay, so mask. So mask means that a mask from a bit. So this is a number that has some bits, and we are storing some mask of this number. So we are storing like 10000 here. So this will be stored here. Okay. So this mask will be equal to some bits that are consecutive, and this indicates whether every box we have unlocked or not. So this means unlocked. This means not unlocked. This means unlocked, and so on. Okay. So we want to store for every box. So if we are standing at box I, we want to store for this box some integer, some mask, some bit mask that have only bits of zeros and ones that have an set bits of the boxes that can unlock. Okay, so we have something like boxes of size m, and then after we took b, so b, if b equals to something like, let's consider, so if b equals to something like 3, then I want to set the third bit in boxes of I, right? So I want to make boxes of I, want to set third bit. So for boxes of I, I want to, so okay, so for boxes of I, for this i's key, I want to set the third bit in these boxes. Okay, so how could we make this? So initially boxes of I will be equals to 0, and then I want to choose the third bit and then set it to 1. How could we make this? With the OR operation. Okay, so we all know the OR operation makes this. So 1 or 1 gives us 1. 1 or 0 equals 0 or 1 gives us 1. And 0 or 0 gives us 0. Okay, so if I have 1 and ORed it with anything, then it will give us 1. Okay, so I'll just OR boxes of I with 2 power 3. Okay, actually it should be 2 power 3 minus 1, because 2 power 3 minus 1 will set the third bit. Okay, so I'll just make this boxes of I or equal 1 shift b minus 1. Okay, so do you know what do you know the shifting? Do you know how shifting works in computer? Okay, so one power x, one shift x is the same thing as 2 power x. So this is equals to 2 power b minus 1. Okay, so what the shifts does, so 1 shift 0 means that I put 1 here. Okay, 1 shift 1 means that I'll put 1 here. 1 shift 10 means that I'll put 1 at the 10th bit or the 9th bit in some integer. Okay, so shift just shifts the number by this value. Okay. Actually, it says that my connection is not stable. Can you all hear me? Can you all hear me and see what I'm writing? Okay. Okay, so here I'm saying that 1 shift b minus 1 equals to 2 power b minus 1. This is the same thing. So I'll make here boxes of I or equal 1 shift b minus 1 just to set the 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 bit that's located at the third position. Okay. So if you're wondering why I'm saying b minus 1 not b, because we are starting from 0. So if I have an integer like this, so the first bit is 2 power 0, the second bit is 2 power 1, the third bit is 2 power 2. So if I want to set the third bit, I'll OR 2 power 2. Okay. So now after I finish taking all these boxes, I'll have the boxes array something like this. If I call boxes of 2, so the second key would be something like this. Okay. So that means that it can unlock this box and this box and this box and this box and this box only. Okay. And all of these boxes it couldn't unlock it. So if I have some boxes, so here box 3 and here box of 5. So 2 and 3 and 5, this represents the key index. Okay. So if I want to check the second key, the third key, and the fourth key, and there's something like this. Okay, so if I took the OR of all of these boxes, so if for example I'm here, I solved the DP function and just ORed all these keys together. So if I choose all these keys together, then I'll just make this or this or this, and the value of this will be equals to, so 1 or 0 will be equals to 1, and here there is 1, so it will be 1 1 1 1 1 1 1 1 1 1. Okay, so if I ORed all of these boxes, all of these values together, it should give me 1 1 1 1 1, and that means that I have unlocked all the boxes. But if I have this bit is 0, so then I have 0 here, 0 here, 0 here. So the ORing of them will be 0. So this will be not true. Okay, so we will cannot we won't unlock all the boxes like this. Okay, so I want to make sure that that at the end, after choosing some keys, I'll have some integer like this, exactly like this. Okay, so for the DP here, I'll just let's make a memoization array that will be of size m times m. Okay, so what's 2 power 12 equals? 2 power 12 is 4096. Let's make it 4096. Okay, so because this integer can go up to 2 power 12, so it will be up to 4096. And then here, to solve, let's forget about the base case now. So to solve for any I and for any mask, we'll have an integer r equals to memo of I of mask. First, of course, we'll memset the memo array with -1, means that we have not reached any state yet. So if r equals to -1, so here if r equals to -1, that means that memo of I of mask equals to -1. And if it's equal to -1, then I didn't visit it. Okay, and if I didn't visit it, then I want to calculate again. So how to calculate this? So it will be r equals to minimum of solve I plus 1 mask. So solve I plus 1 mask means that I just went to the second key without taking anything, without taking this key. But if I took this key, then I'll return cost of I plus solve I plus 1. So if I took this key, then of course I'll add the cost to this key. But what should I pass here to the mask? So I shouldn't pass mask as it is. So I should OR it with boxes of I, right? As I said here. So I'll pass mask or boxes of I. Okay. So can you understand this? So this, how can we get the answer? That's it. So it will be the minimum between two cases. So either take the box, either take this key, and then don't either take this key and then take all of its boxes, or not take this key and not take any of its boxes. And for this case, it's easy. I'll just go to the next state without taking this box. But if I took this key, I'll take all of the boxes assigned to it, and I'll OR it to mask, and I'll add the cost. Okay. But what about the base case here? So the base case here is when I reach I equals to m. So when I've passed through all the keys. So if I equals to m, because I started from I equals to 0, then I equals to m means that this is after the last key. Okay. So if I'm after the last key now, I'll check if mask all ones. So if mask something like this, so it should have all ones, then I'll return okay. Okay, I'll return 0. Okay, and if it's not, if it has some 0 here, then I'll return a very big value. Why return a very big value? Just to make this case false. So if I return a very big value, then it won't be minimum. Okay. So that's it. But how to check if the number have all of, or if the number have all ones like this? Let's think about it. So to check if a number has all ones like this, we have n here, so we know the size of this mask. Okay, so the size of this mask, for example, if it's 12, then it will have 12 bits. 1, 2, 3, 4, 5, 6, 7. Let's make it once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the size of this mask is 12, and I want to check if this mask has all ones or not. It's easy. I'll just OR it with another integer. I'll just OR it. I'll just XOR it with another. Do you know what XOR does? Okay, I'll just explain it.
Same
Uh,
it is 0.
Yes. What did you say? I cannot hear you.
When all bits are same, means when it will become 0. So when it is
Yes.
1 1, it will become 0. When it is 0 0, it will become 0.
Yes. So XOR returns 0 if they are the same. Otherwise, it returns 1. Otherwise, it returns 1. Okay. So if I took of these two numbers, if they return 0, then I'm okay. Then this mask is okay. But if this mask have some 0, then if I took the XOR of these two numbers, then it won't return 0. Then I'll not be okay, because here I'll have 0 and 1, then it will be 1 here, and here 0 and 1, then there will be 1 here. So I'll just check. I'll just have this number. So how to get this number? This number equals to, okay. So this number equals to 1 shift n minus 1. So why is that? If n equals to 12, so 1 shift n equals to 2 power 12. So let's make it here. 2 power 12. So 2 power 12 is something like this. This is exactly 2 power 12. Okay, but 2 power 12 minus 1, I'll remove this one and put 1 in all of these bits. Okay. So this value equals to 2 power 12 minus 1. Okay, so it could be proved with geometry sequence, but it's a well-known thing. Okay, so if I took any power of 2 and then subtracted 1 from it, then I'll have all the bits before this power set. Okay, so that just to check this, I'll say if mask. So the XOR in C++ is used like this XOR. Okay, so if mask XOR one shift n then minus 1 equals to 0. So if it's all then equals to 0, then I return 0. Okay, else return something big. So I'll make an integer big here equals to something like 1e8. This is a very big number. Then I'll return 1e8. So let's check for the problem what's the maximum number I could get. So it will be 10 power 3 times 10 power 8. So the maximum cost that the problem will give us will be 10 power 3 times 10 power 5, which is 10 power 8. So I make this slightly bigger, 1e9. Okay. So if this is returned, if some number is very big is returned like this, then it's not okay. Okay. So that's it. That's our DP function. Let's recap this DP function again. The states means that I'm standing at the ith position, and this must means that before what boxes that are selected before the ith position. Okay, so here to calculate this state, I'll take the minimum between uh, either taking this box and add the cost to it, and then going to the next state, I'll order the box with I with mask, or not taking it at all. Okay, I think this is easy. And if at the base case here, if I reach the end, then I'll just return 0 if I have everything once. Okay, so if mask or 1 minus 1 equals to 0, then I return 0. Otherwise, I return big. Okay, so here I'll just print solve. I'll start from 0, so I will be equal to 0, and the mask also will be equal to 0. Okay. Okay, so here there is something. If it's impossible to unlock all of them, print -1. When will it be impossible? So if it's impossible, then I'll always return 5, because if it's impossible, then there will be no state that will return 0. It will always return big. So I'll have to here, and then I'll have to check if answer is very big, then I'll just print -1. So if answer greater than or equals big, then answer equals to -1. Okay, and then I'll print answer. That let's check the code again. I'll just revise it. Okay, so there is something here. So I'm taking T, which is the cost, and then B, which are the boxes. So I'll just have to make this while B minus minus. So while B minus minus, I'll take another integer which refers to the box that I'll order it with. Let's call it bits. And then I'll order this with bits. Okay. So here I'm taking B, the number of boxes, and then I'm looping through the number of boxes, and then I'm ordering every box. Okay. Okay, everything should be okay. guess. Just bugging. Yes, I'm taking it. So the minimum should be 25. It returns then. Let's check the base case. If mask so one sheet and minus one possible I will return it. Is my screen lost or do you see it?
We can see.
You can see my screen?
Yeah.
Should be visible. I think you should see it now. Should see Visual Studio, right?
Yeah.
Okay. Okay, let me check the code very fast. Okay, let's try another order.
Since you're taking, would it be unsigned?
Since I'm taking what?
Since we are taking the bitwise operators, should it be unsigned integer, not is that making difference?
No, it won't make any difference. Because our values is always positive. There is no negative numbers here. Okay. I'm sure that it's a very small bug. I'll get it now. Okay. Sorry for this. Mm. Let's make this a bit smaller. Okay, this should be working. Hmm. I think the input, I'm taking it wrong. So read this post. Read it. Okay, I'll just spend another 1 minute debugging this, and if the problem I cannot see it, I'll just move to the next problem and send you my last code. It's got accepted. Just don't waste time. Okay, I'll just give you my last code that it's the same as this. Um, but this should get accepted. Okay. So here is the code for the problem. The code that I solved the problem through it should should be the same thing, pretty same. And then we'll move to a next small problem. Okay. Okay, since there is a meeting after 10 seconds, I'll have to finish in these 10 minutes. I'll spend 2 minutes to look through the code, and I'll send the link to my last code of this problem. Check it until I get the bug for you now. Just
But I can see one difference in your code and the submitted code over here.
You
The
cannot see the code?
no, I can see like when you're taking the input in line number 33.
Line number 33.
Yeah, line number 33 in the code which you are given is like you're shifting that without anything, like one left shift bit, not bit minus one.
Yes, it's the same thing because I'm just subtracting one from the number before. So I'm just making like this. Bit minus minus. Right? This is what you mean, right? So this is the same thing. Okay, I'll try it again. It's equals to -1. Okay, so these kind of bugs just come, and they might be very tiny point that I didn't consider, but the code is the same. So as you look, so the idea is the same. I might find the bug afterwards, but I gave you my accepted code here right now. Okay. Okay. So since we have no time for another question, I'll give you another two homework questions, and then for the next time we'll discuss them and solve more. Okay. Oh, so the bug was this is this is so bad. The bug was something that I didn't know at all. So I just put brackets here. Can you all hear me? I
Yeah.
think
Yes.
yes. Okay. Okay. So I don't know why this, but in here in C++ programming language, so I'm just if I'm saying mask XOR this equals to 0, then things get messy without putting brackets. So this is calculated before this or something like this. So I'm just adding brackets here. This is a very silly mistake. So I added brackets here to make sure that this value is compared to 0. But without brackets, this total value is not compared. So with using XOR and 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 OR operations, these build operations, you must put brackets everywhere to make everything okay. Okay, let's try here. Okay. Okay, it's working now. Okay, let's submit the code. So my screen is gone now. Okay, you must be seeing my whole screen now. Okay. Everything should be fine. Okay, accepted. Here's the code. Here is the new code in the chat. Okay. So before moving on, do you have any questions in this code? I know that there is DP and there is so there are bits and there are some things that you might not get quite fast. So do you have any questions in this code, in this problem? Yes, say if you have any queries, anything. Okay, so no questions? Okay, if you have any questions, say. I'll give you the two homework problems. Let's take. Here's the first one. Here's the second one. So one hint that these two problems, the two of them, have common ideas or use common things that we used from the two problems today. Okay, so these two homework problems have some common things that we use today. So you should be able to solve them all. Okay, and the next time I want to see you solving this problem and just tell me the whole idea to make this thing more interactive. And you have to practice more with yourself. So just looking on solved problems doesn't make a strong competitive programmer. Okay, so you should to develop your problem solving skills, you have to solve more problems with your own. Okay, so I strongly advise you to solve these problems completely. Okay, so these two problems, try to solve them completely. The next time we'll discuss them. Okay, any questions before I leave?
Hello.
Hello, yes.
Yes. Actually, I'm preparing for the interview. So these kind of problems are asked in
Yes.
interview.
Yes, so we are solving these problems just to develop your problem solving skills. So we have solved DP problems, uh, some observation problems that require some problem solving skills. So for interview, yes, for sure, they will make you very strong for the interviews. And it will make you very strong more than the ones who just know the basic algorithms and don't develop their problem solving skills. Okay.
So
What's
one more thing, like these are I found the last question you solved it bit difficult. So to become more comfortable in these kind of problems, shall I start with the basic problems and then go to the difficult one? Like, what do you suggest?
Yes, I strongly suggest this. So, did you find the first problem good for your level?
Yes, first problem was quite easy. Means I would have solved it myself.
Okay, so the thing is that these problems are varying in difficulty from person to person, and someone might see this problem easier than another problem. So to be strong enough, you must solve many problems. So
So
if you find, yes, I know, I understand you. So if you started easy, just very easy, like the problems you are comfortable with, you won't get developed. And since we are here, I'm solving problems that match all of your levels. So I cannot solve easier problems, but you can solve. I strongly advise you to solve with your own problems, like the first one I solved, and then somehow after solving many problems, you will be able to get to these hard problems and solve them with yourself. Okay.
so what's means do you have any site in your mind that I can go through and solve? Means where I can find these kinds of problems?
Okay, so the best thing to do is to participate in online contests in codeforces at coder coach F. I'll send the links here. So this is codeforces.
So is it free of cost
And
or
this is
we have
coach F.
to?
Hi guys, we have one more session and we'll be using same meeting. So I mean the time is already over. Probably we can continue next time, and
Okay.
probably I'll be sending you all the details after taking those websites link, and how should we approach all those things. I'll be sending you mail. So
Okay.
sorry I have to hard stop at uh, now because the people in the other meeting are waiting.
Okay.
So uh, right, so just can I'll be in touch with you after the meeting regarding how you can proceed and what and all website you can follow.
Okay. No problem.
Okay. Since we should end now, next time we will talk about these things and just make sure to solve these two homework problems. Okay, and next time we'll talk about how to get better at these problems. Okay.
Okay.
Thanks all for joining.
Thank you.
Okay, thanks a lot.